Welcome back to Basic Electronics. In the last lecture, we had started looking at the instrumentation amplifier. We will continue with that discussion. We will see how the instrumentation amplifier is better, both in terms of input resistance and common mode rejection. We will look at two additional op-amp circuits in this lecture, the current to voltage converter and the integrator. So let us start. The input resistance as seen from Vi1 or Vi2 is obviously large because we are looking into the op-amp directly, and the op-amp has a large input resistance, and therefore this instrumentation amplifier will not load the preceding stage, and that of course is a very desirable feature. In other words, it will not draw any current when we connect it to for example the bridge circuit that we have seen earlier, like that. So now when we connect the amplifier to the bridge circuit, this current is almost zero, and therefore V1 will not get disturbed. This current is also zero, so therefore V2 also will not get disturbed. And now when we make the measurement, we can expect our VO to be what it really should be. So the voltages V1 and V2 in the bridge circuit will remain essentially the same when the bridge circuit is connected to the instrumentation amplifier. So the instrumentation amplifier is definitely superior to the difference amplifier because it offers a much larger input resistance, and therefore when we connect this to the bridge circuit, for example, these voltages Vi1 and Vi2 will not get disturbed, and therefore our measured output would be a true reflection of what we are trying to quantify. Now let us look at the other important issue, that is the performance of the instrumentation amplifier with respect to common mode input voltages. As we have seen before, Vi1 and Vi2 can have a large common mode component. Vi1 is given by Vc minus Vd by 2, Vi2 is given by Vc plus Vd by 2, and we have seen earlier in the bridge circuit example that Vc can be quite large, for example 7.5 volts there, and Vd was only 37.5 millivolts in that example. And now we want to know what is the effect of this common mode input voltage on the amplifier output VO there. When we look at the common mode rejection performance of the instrumentation amplifier, we will assume that the op-amps themselves are perfect. That means they have very high CMRR, infinity. So the finite CMRR of the instrumentation amplifier as a whole will arise only because of resistance mismatch. So this R2 and R2 prime are supposed to be the same, but they would not be exactly the same because of tolerance values. Similarly, this R3 and R3 prime would be slightly different, and R4 and R4 prime would be slightly different. So as a result of that, the instrumentation amplifier will have a finite CMRR, and that is what we want to find. Let us note that VO1, this voltage, serves as the input Vi1 of this difference amplifier, and similarly VO2 serves as the input Vi2 of the difference amplifier. And now we will find the differential mode and common mode components of this input voltage. What is the differential mode input voltage? We will denote that by Vid prime, so that is equal to VO2 minus VO1, VO2 minus VO1, and the common mode component Vic prime is half VO1 plus VO2. What is Vid prime? It's VO2 minus VO1, so it is this voltage drop plus that plus that. So it's R2 prime plus R1 plus R2 times I1 with a negative sign because we are looking at VO2 minus VO1. What is I1? It is VA minus VB divided by R1, and VA itself is VI1, which is the same as VC minus VD by 2. VB is the same as VI2, which is VC plus VD by 2. So when we put all that together, we get this expression here, and VC cancels out, and we are left with 1 plus R2 prime divided by R1 times VD. So that is our differential mode input voltage as seen by the difference amplifier. Let us now look at the common mode voltage seen by the difference amplifier, and that is half VO1 plus VO2. So that is half. This is VO1. What is VO1? It's VA plus this voltage drop, that is I1 times R2, and VA is VI1, which is VC minus VD by 2. So VC minus VD by 2 plus this voltage drop I1 R2. What about VO2? It is VB, which is the same as VI2, which is VC plus VD by 2, minus I1 R2 prime. So that is VO2. And now we see that this VD by 2 of course gets cancelled. VC plus VC is 2 VC, and this I1 times R2 minus R2 prime is a very small quantity because R2 and R2 prime are actually supposed to be matched, and their difference would be negligible compared to VC. So therefore overall we have VIC prime nearly equal to VC, the common mode voltage at the input of the instrumentation amplifier. So something very significant has happened. Let us see what that is. At this stage, our common mode voltage was VC and the differential mode voltage was VD, and that is why VI1 was given by VC minus VD by 2, VI2 by VC plus VD by 2. When we come here, our differential mode input voltage has got amplified, 1 plus R2 prime divided by R1, and this gain could be substantial, could be 20, could be 50, whereas our common mode input voltage has remained equal to VC, and that of course is a very big advantage. So in short, VD has got amplified but not VC, and therefore that leads to an overall improvement in the CMRR. Okay, so we have come up to this point, and now we want to see what the output voltage of the instrumentation amplifier is. Let us take the simple case first, in which there is no resistor mismatch. So R4 and R4 prime are equal, R3 and R3 prime are equal. In that case, this is a perfect difference amplifier, and its gain is R4 by R3. So therefore the output voltage would be R4 by R3 times VO2 minus VO1, and the common mode component of VO1 and VO2, which is VC, will get cancelled out, and we will get an amplified version of this quantity at the output. So at the output we will have no common mode voltage at all, and therefore the CMRR of the entire instrumentation amplifier would be infinite. In real life, of course, the resistor mismatch in the second stage needs to be considered, but it will surely have a limited effect, and let us see why. Let us compare two cases. One in which this difference amplifier gets VI1 and VI2 as inputs directly without this stage, and in that case, what is the common mode voltage it sees? It is VC. What is the differential mode input voltage it sees? It is VD. That is case 1. Case 2, the instrumentation amplifier. Now what is the common mode voltage it sees? It is VC. And what is the differential mode input voltage it sees? It is an amplified form of Vd, and that is the difference. So therefore the overall gain that the common mode voltage goes through is much smaller relative to the gain that the differential mode voltage goes through, and that gives us much better performance than the plain difference amplifier that we have seen before. Let us now look at current to voltage conversion, and that is relevant because some circuits produce an output in the form of a current, and it is then convenient to convert this current into a voltage for further processing. For example, we might want to display that voltage, or we might want to amplify it further, and so on. Now, what is the simplest way of converting a current to a voltage? Just pass it through a resistor. So this is our signal current Is. We pass it through a resistance R, and that produces an output voltage Is times R, and that's exactly what we want. We have got a voltage which is proportional to our signal current. Fair enough, but there is a problem with that approach. Let us say we want to now amplify or measure this VO1 by connecting an amplifier between this node and ground, like that. This is our amplifier with a voltage gain of AV. So we would expect this VO2 to be AV times VO1, which is AV times Is times R. Now that is not what happens, because this amplifier has an input resistance Ri which comes in parallel with R, and therefore this VO1 would now change to Is times R parallel Ri, like that. And that of course is not desirable. And why did this happen? Because this amplifier has loaded our source circuit. So let us now look at an op-amp circuit which avoids this problem. Here is an op-amp circuit which can be used to convert a current to a voltage. How does it work? It's very easy to understand. This current is 0 because that's an input current for the op-amp, and therefore our signal current Is would go through this resistance R, and VO would then be V minus this voltage drop. And since V minus and V plus are nearly equal, assuming the op-amp to be operating in the linear region, this node is at virtual ground, so therefore VO would be 0 minus Is times R, like that. And note particularly that the load resistance simply does not enter this equation. So this relationship is independent of what we connect as the load, and that of course is what we wanted. Let us take a look at an example, that is a photocurrent detector. What is a photocurrent? Photocurrent is a current that we generate by shining light on a semiconductor device, typically a diode. These diodes of course are specially made, but they are basically the same as a PN junction. Okay, so let's look at the circuit. Here is the circuit. This V bias is negative, let's say minus 5 volts. This node is at virtual ground, so the N terminal of the diode is at 0 volts and the P is at minus 5 volts, for example. So therefore the diode is under reverse bias. In this situation, if we shine light on this diode, this reverse current can change significantly, and that is our signal current. So what is the output voltage in this case? This I prime would also go through this R like that, and therefore VO is 0 volts plus this voltage drop, that is I prime times R. So that's a common application of this current to voltage converter. Here is another useful op-amp circuit. Let us see what it is doing. We will assume that the op-amp is operating in the linear region. So V minus and V plus are nearly equal. Therefore, this is at virtual ground. That gives us I1, Vi minus 0 divided by R, or Vi by R. Since I minus is 0, that's an input current for the op-amp. The current through the capacitor is also I1, like that. And what is the current through a capacitor? It is C dVc dt. So therefore, we have C dVc dt equal to I1 equal to Vi by R. Now we want to relate Vc and Vo. What is Vc? It's V minus minus Vo, and we know that V minus is 0 volts. So therefore, Vc is 0 minus Vo. That is simply minus Vo. So instead of Vc here, we can put minus Vo. So that gives us this equation: C times minus dVo dt equal to Vi by R. In other words, Vo is minus 1 over RC integral Vi dt. And we see that this circuit is working as an integrator. So it integrates the applied input voltage. Let us look at an example of the integrator circuit. Given R is equal to 10K, C equal to 0.2 microfarads, and the input voltage waveform is given. It is 0 up to this point, up to 0.5 millisecond. Then it rises abruptly to 5 volts. Then it remains at 5 volts up to 1.5 milliseconds. And then it comes down to 0, stays at 0 thereafter. That is our input voltage. We are also given that the output voltage, this, is 0 at t equal to 0. And given these conditions, given these component values, we want to find Vo as a function of time. Let us use t0 to denote this time at which Vi is going from low to high. So t0 is 0.5 milliseconds, and let us use t1 to denote this time at which Vi is going from high to low. So t1 is 1.5 milliseconds. Alright. Now what do we know about the integrator? We know that Vo is given by minus 1 over RC integral Vi dt. This RC we will denote by tau. And what is the value of tau? R is 10K, C is 0.2 microfarads. So 10 times 0.2 is 2, kilo times micro is milli. So tau is 2 milliseconds. What we will do now is to consider 3 different intervals. This one, that is 0 to t0, this one from t0 to t1, and this one, that is t greater than t1. And in each of these intervals, we will find Vo of t, and then finally we will put it all together. Alright, so let us start with this first interval, that is t less than t0. So what we can do now is to evaluate this integral from 0 to t, where t is somewhere in this interval. On the left hand side, we will get V0 of t minus V0 at 0. And on the right hand side, we will get minus 1 over tau integral 0 to t Vi dt, and Vi is 0 here. So therefore, this whole right hand side becomes simply 0, and therefore Vo of t becomes equal to Vo of 0, that is 0 volts, as shown here by the red line. Next, let us consider the interval from t0 to t1, that is 0.5 milliseconds to 1.5 milliseconds. Throughout this interval, Vi is constant, 5 volts. So let us find the output voltage now. Again, we integrate Vi from t0 to t, and on the left hand side we will get V0 at t minus V0 at t0, and on the right hand side we'll get minus 1 over tau t0 to t integral Vi dt, and Vi is 5 volts, so therefore this turns out to be minus 1 over tau 5 times t minus t0, and this is simply a straight line. This is our y, this is a constant, and this is our x, so it has the form y equal to mx plus c. So that's a straight line, and as we can see it has a negative slope, minus 5 divided by tau. So we expect VO to go down at this point, a straight line with a negative slope, so something like this. And now let us calculate what VO should be at T1, that is 1.5 milliseconds. At t equal to T1, all we need to do now is substitute t equal to T1 in this expression. So VO at T1 minus VO at T0 is equal to minus 1 over tau, tau is 2 milliseconds, times 5 volts times t minus t0, that is T1 minus t0. T1 is here, t0 is here, so T1 minus t0 is 1 millisecond, so that is 1 millisecond. So this turns out to be 5 divided by 2 or 2.5 volts. This milliseconds will cancel with this milliseconds and we are left with minus 2.5 volts. So that gives us the output voltage at T1, and that is what VO of t looks like up to t equal to T1. After this point the input voltage is 0, and therefore this integral will be 0, and therefore VO will not change. So for t greater than T1, VO remains constant since Vi is equal to 0 volts, like that. So that is our overall VO of t. There is a circuit file available for this example, and you can check out this simulation. You can try to increase this capacitance, for example, from 0.2 microfarads to 0.5 microfarads. Work out what you expect for VO and then simulate and check whether your prediction is correct. You can also try to change this Vi from 5 volts to, let's say, 3 volts. Again, work out VO of t and check if it is according to your prediction. What we saw previously was a simple example just to get used to the numbers and the action of the integrator. But an integrator can actually be used for doing something very useful, and that is to convert a square wave to a triangle wave. So here is our input square wave going from minus 5 volts to plus 5 volts with a period of 2 milliseconds, and that is our output triangle wave. And with these numbers you should really work out what VO of t is going to be and check that this plot is indeed correct. Now in practice this circuit will not work in its present form, and we will see what the reason is. It will require a small modification, and we will also discuss that modification. But the basic idea is borne out very clearly in this graph. A square wave input and a triangle output. Again, the SQL circuit file is available for this circuit, and you can check out the results. To conclude, we have seen that the instrumentation amplifier offers a high input resistance and a high CMRR, and that makes it well suited for sensor applications. we have looked at two additional op-amp circuits, the current to voltage converter and the integrator. In the next lecture, we will look at some non-idealities associated with an op-amp and how they can affect the circuits we have considered earlier. So see you next time.